Welcome viewers to this video on differentiation, particularly maxima and minima. I'll do exercise 8.6, page 203, book 4, mathematics. Now the first question is going to involve the following. The height after t seconds of an object thrown vertically upwards is given by s equals to 4.9t minus t squared. Find the maximum possible height it reaches. Okay. So I'm going to handle the solution here. So I'm going to draw this kind of representation. This is the stone which has been thrown vertically upwards, and then the height here, or the displacement, is equals to s equals to 4.9t minus t squared. Okay, so we are determining the maximum possible height it reaches, but then for us to do that we need to differentiate s with respect to t in order for us to get the velocity, which we are going to set equal to 0, and then use that time that you're going to obtain there and substitute in our displacement function and get the maximum height. Okay, so we are going to say ds over dt is going to be equal to 4.9 minus 2t. That is, when you differentiate 4.9t, you get 4.9. When you differentiate t squared, you're going to get 2t. So we set this equal to 0 and we solve for the value of t, which is nothing but 2.25 seconds. Okay, so with these 2.25 seconds, we substitute them back to our displacement function, and this is going to give us 4.9 into 2.25 minus 2.25 quantity square. Okay, so this is going to give us what? When you multiply, you're going to have 11.025 for this part here, and then this part is going to give us 5.0625. So when you subtract, you're going to have 5.9625 meters. So this is the distance all the way from this point to where it gets, that is the maximum point up here. So that's the answer for the first question. Back to go to the second question here, which is going to involve a piece of wire 18 centimeters long is bent to form a rectangle. If its length is x centimeters, obtain an expression for its area in terms of x. Hence, calculate the dimensions of the rectangle with the maximum area from the expression. Okay, so I'm going to continue from this point here. So it's always good to have a geometric intuition of how that problem looks like. So this is why I draw this figure here. So this is my rectangle. We are told that the wire that is going to be bent to form this rectangle is 18 centimeters. Now from here we are going to get x centimeters and then x centimeters, because these two sides are the same, they are equal in other words. Then we take away the sum of these two from 18 and we are going to have 18 minus 2x. But of course this 18 minus 2x, which is the remainder piece of the wire that was there, we are going to share this equally so that we can have the length of this rectangle. So by so doing, this one gives us this nice looking rectangle, which is 9 minus x, and here we have x, so the units in centimeters. So now we need to determine the expression for the area of that rectangle. So we are going to have area equals to length times width. So length is 9 minus x, width is x, so this gives us 9x minus x squared. So we have that. So if you differentiate area with respect to x and you set that equal to 0, you're going to get the dimension that is going to give you maximum area. Okay, so differentiate this function with respect to x, you're going to have 9 minus 2x. Okay, upon setting this 9 minus 2x equals to 0, we are going to solve for x, which is 4.5 centimeters. Now if x is 4.5, you can substitute back here to get the dimension. So this is 4.5. 9 minus 4.5 is 4.5 centimeters. So those are the dimensions that would give a maximum area from the 18 centimeters piece of wire. Okay, so let's go to question number 3. I'll read the question. A man has 75 pi centimeter square sheet of metal and wishes to make an open cylindrical container with it. Find the dimensions of the tin for which the volume will be maximum. Okay, as usual, I'm going to make a diagrammatic representation of my cylinder here, and then I will take my radius to be r and my altitude to be h there. Okay, so I am interested in determining the dimensions of this tin that will make the volume maximum. But of course I'm told that this cylindrical container is open on the upper side, so I'm going to get the area of the bottom side and the curved surface area and equate to 75 pi. So 75 pi is going to be equal to pi r squared, so this is the area of the base, plus the curved surface area, which is 2 pi rh. Okay, so I'm going to make h the subject of the formula, but before then I can see that pi hangs loose, so I can divide by pi everywhere. So I have 75 left on the left hand side equals to r squared plus 2rh, and then taking away r squared from both sides, I'm going to have that. Then I divide by 2r by 2r, so h is nothing but 75 minus r squared over 2r. Okay, so I'm going to come up with an expression for the volume, because it is the volume that has to be maximum. So as we all know that volume of a cylinder is pi r squared h, and so this is nice because now where I have h, I'm going to substitute with 75 minus r squared over 2r, so that the whole expression will be purely in terms of r. So I have v equals to pi r squared, then we have 75 minus r squared over 2r. So this one can simplify into 75 pi r squared minus pi r to the fourth over 2r. Okay, so r is common, so we can factor that and divide. So we have 75 pi r minus pi r cubed over 2. Okay, so that is the expression for the volume. Now let's get the derivative of volume with respect to r. So dv over dr, we can see 75 pi over 2 minus pi r cubed. Some of the constants can hang loose, so we can take them out. So I can take let me take pi over 2 out. So I'm going to differentiate 75r, so that is 75, minus here I'm going to have r cubed, differentiate that, you have 3r squared. Okay, so I know I have to set dv over dr equal to 0 for me to get the value of r, which makes the volume maximum. I know when I set this equal to 0, pi over 2 is not equal to 0, hence this part is the one that is going to be equal to 0. So we have 75 minus 3r squared is 0, so 3r squared is 75, so by 3 both sides, that gives me r squared is 25, so r is plus or minus 5. And since r cannot be negative, we are going to take r equals to 5 centimeters. Now we are not done yet, but you're almost there, because we need to determine the value of h, because here h is in terms of r. So we take h is equal to what? We take 75 minus 5 squared, so that is 25 over 2 times 5. So if you simplify this, it will give you 75 minus 25 over 10, which is 50 over 10, which is 5 centimeters. So you can see that both radius and the height of this particular cylinder here, they are the same. But then the question was, we determine the dimensions of the tin for which the volume will be maximum, and so the answer is h equals to 5 and r equals to 5 here. So I think we go to question number 4, this one there. So question number 4 reads, the distance s of an object from a fixed point is given by s equals to a third t cubed minus 3 over 2 t squared. Supposed to show that the velocity is minimum at t equals to 3 over 2 s and find this velocity. Okay, so given the expression for displacement as a third t cubed minus 3 over 2 t squared. One thing I know is that we are moving from a given point to another point, and this is what defines the displacement. Then we need to determine the velocity of this body from this point here, and then find the second variation of point, which is acceleration, and then that will give us time that we're going to have so that we can show that it is equals to 3/2. Okay, so let's take the derivative of this displacement with respect to time and determine v, which is going to be t squared minus you have 3t. Okay, if you differentiate this, you're going to get t squared minus 3t. Okay, so this is v. Now we need to get acceleration, which means that if you're moving from displacement to velocity, you differentiate. You're moving from velocity to acceleration, you differentiate, and vice versa is integration. So we are moving from velocity to acceleration, so we differentiate v with respect to time for us to get a, and this is 2t minus 3. So we set this equal to 0 and we are done. So we say 2t minus 3 equals to 0, so 2t is 3, so t is equals to 3 over 2. You notice this is what we were told to show, that the velocity is minimum at time equals to 3/2, and that's the answer. So we need to find now the velocity of this point that was moving. So we have of this body that was moving. So we are going to go back to the expression for the velocity, which is v equals to t squared minus 3t, and in it we substitute 3/2. So you have 3 over 2 quantity square minus 3 into 3 over 2. Well, this is like 9 over 4 minus 9 over 2, and we are going to have this equal to what? We have LCM is 4 divided by 4, 1, 9 minus 4 divided by 2, 2, then times 2 you have 18, this is negative 9 over 4, and that is negative 2.25 meters per second. So the velocity is allowed to take a negative value because it is a vector quantity, so we have negative 2.25 meters per second. Now let's go to question number 5. So Onyango wishes to fence a rectangular research plot using 100 meters of wire. One end of the plot has a wall already erected. Calculate the maximum area that he can fence. Okay, so again, as usual, I'm going to assume that we have this plot, but of course one side is fenced, so I'm going to assume this is not requiring the fencing because it's already fenced, but of course the piece of wire is 100 meters long. So if I assume that this side takes x meters, also because this is a rectangle and these two sides are equal, it will take x meters. So this side will take 100 minus the sum of these two, okay? And that will make now the sum of these measurements to amount to 100, because if x plus 100 minus 2x will be 100, and that's equal to the total length of the wire. So we have to express this one in terms of area of a rectangle, so we have area is length times width. So length is 100 minus 2x and width is x. So if you multiply, you're going to have 100x minus 2x squared. Don't forget that we want to calculate maximum area, and that can only be achieved if we set the derivative of area with respect to x equals to 0 and then get the dimensions. So we have dA over dx is equals to 100 minus 4x. Okay, so we set this equal to 0, so 100 minus 4x equals to 0. We have 4x equals to 100 and x is nothing but 25 meters. Okay, now upon getting x equals to 25 meters, so we know that this side has 25 meters, equally this side has 25 meters. So if this is 25, 25, this side must be 50 meters, so that we can have 25, 25, 50 to amount to 100. So what is the area of this plot? Now, having known the dimensions, then we know it is 50 meters times 25 meters, which is going to give us 1250 meters square. Okay, that is quite easily done. So let's go to question number 6. Okay, right, so question number 6 reads, a rectangle is inscribed in a right-angled triangle ABC. Show that the area of the largest such rectangle is half the area of the triangle. So this is the key point to note. So I'm going to draw the triangle here, and in it I'm going to have my rectangle. So this is the rectangle. I'm going to assume that my altitude of this triangle is h, and my base is nothing but b. Okay, so that now my length of the rectangle is x and the width is y. So just a reminder, area of a rectangle will be xy, because it will be the length, that is length times width. And then the area of a triangle, it's good to note, supposed to be a half base times height. Those two are going to be handy in our process. So the first thing I'm going to do for me to achieve that, I already have the dimensions of the triangle and the rectangle respectively, but of course I want to use the concept of similarity and enlargement. So this part here, I'm going to call this one h minus x. H minus x. Why? Because from here to here is x and the entire height here is h. So for us to get this point here, we have to take away x from h. Okay, now using that, I'm going to compare these two triangles. Let me just be quite explicit a bit. So this is h minus x and this is y. So this is the smaller triangle here, and they are all right angled. Then I compare this vis-a-vis the bigger triangle, which is having a base of b and an altitude of h. Okay, that's clear. So those triangles are going to be assumed to be similar. Now if they are similar, we got to compare these two. So we compare altitude. We have h, that is the height of the bigger triangle, over the height of the smaller triangle, which is this part here. Then we compare with the base. The base of the bigger triangle is b, and the base of the smaller triangle is y. So upon doing that, we can cross multiply. We have hy equals to b into h minus x. So we have hy equals to bh minus bx. Okay, so I want to differentiate this function after solving and getting the value of y, but of course I need to go back to the formula of the area of rectangle, which is area is equals to xy, but of course x is known, So what I don't know is y, but of course from here I can equate. So I have bh minus bx over h. I think that is clear from that point. So I can see the whole expression now is in terms of x, and x, y is not there. So I can have this one expressed as hx minus bx squared over h. Now I can differentiate now the area of the rectangle, which has to be maximum, with respect to one of the variables, which is x, because this expression involves x. So I'm going to have the following. If you differentiate this, h is a constant, so I care less about it. So we differentiate that, we have bh minus, I'm working on the numerator, minus 2bx now over h. So I got to set this one equal to 0 here, and we are making a continuation of what I'm doing up here. So we have set my working space. So we have dA over dx, that is the derivative of the area of the rectangle with respect to x. I set it equal to 0. Okay, but then of course, because this one is going to happen if and only if the area of the rectangle is made to be maximum. All right, so let's handle that. So we are going to have 0 equals to bh minus 2bx over h. Right, so this now shows that 0 equals to bh minus 2bx. Okay, b is common, so you can factor it out. You have h minus 2x equals to 0. So we have h minus, either of these two is 0, so h minus 2x is 0. So we have h equals to 2x, so x can be a half h. That is vital, so that one we need to take care of. Then we go back to where we said that y is, we say that y is bh minus bx over h, and see what happens. So if you substitute this x here, what happens? We have b h minus b into a half h over h. Now by so doing, this h becomes common, so we can factor h out. We have b minus a half b over h. That's why. So this cancels with that, and this gives us b minus a half b. Again, this is common sense, so it is just a half b. So we can now merge these two pieces of information. We have the first one says that x equals to a half h and y equals to a half b. It's like they're giving us a kind of relationship. Let's see. Now we said initially, if you can remember very well, we said that area of a rectangle is xy, and area of a triangle is a half bh. So we want to show from here, how do we get the area of a rectangle? We are going to have x times y. Okay, so this is the area of a rectangle, which is a half h times a half b, which is a quarter bh. Okay, allow me to do some sort of manipulation here. I know this is like a half of bh. Wait, this xy is the area of rectangle. Then this part here forms the area of a triangle. So we can see that the area of a rectangle that is formed from this triangle up here is a half of the area of the triangle. So we can see it's like we've shown comfortably that the area of a triangle that can maximally be formed from that triangle is a half the area of that triangle, and that is quite easily done. Thank you, keep watching our videos, and in my next video I'm going to handle a problem concerning problems from number 7 all the way to number 10 of the same exercise, and we will come to an end to this point. Thank you.